The vast majority of biological samples that we use for electron microscopy are thin samples. Of course, we have seen that with scanning electron microscopy we can also look at the outer surface of larger samples, but in most cases we look at thin samples. For transmission imaging, transmission electron microscopy or scanning transmission electron microscopy, this is obvious. The sample needs to be thin enough to allow the electrons to be transmitted through the sample and be detected there. But also for scanning electron microscopy, samples may be thin sections. And there the advantage, of course, is also that a thin sample may give access to looking at the interior of a cell. In this case, the signal that we predominantly collect are backscattered electrons. Of course, we can also use secondary electron detector, but we may recall that secondary electrons give us a topography contrast, and in this case for a thin section there's not much topography, so the secondary electron signal will most resemble the backscatter electron signal by secondaries generated by backscattered electrons. Now, this puts a few challenges on the preparation of samples for electron microscopy. Of course, most samples are not thin, so the specimens must be thinned down in order to allow mounting in a scanning electron microscopy for inspection. Also, in the electron microscope, we've seen that there's a vacuum. So most biological samples are hydrated, so we need to either dehydrate the sample or make sure that the sample does not evaporate and shrink while we are inspecting. Also, the electron beam may damage the sample. So radiation damage while we are observing the sample is also a concern. We don't want the sample to change while we are observing it. Typically for biological samples, the signal to noise may be very low. We've seen that carbon materials generate only very few backscattered electrons, so we may need to add contrasting agents to up the signal, or if we look at phase contrast in transmission electron microscopy, typically we're also in the regime of very low signal compared to the background and the noise. And finally, of course, the samples will be insulated, so charging may also be an issue. So we can formulate the goal of sample preparation as the need to preserve the biological sample in a native or as close to native as possible state. So the state at which the sample will be when we put it in electron microscope, in vacuum, during radiation, with radiation damage going on, must still be as close as possible to the native state. And this preservation should be such that in the end we will get the maximum contrast for the sample. So the maximum contrast will assure that our illumination time is short, so that we get highest resolution with the least amount of data, meaning the least amount of exposure and thus the least amount of damage, preferably no damage to the sample. So the first thing that we need to do in the sample preparation is to fix a sample. Say we have a cell culture or we take a tissue from a human or from a model animal, we need to fix it as quickly as possible in order to follow the further sample preparation steps in order to allow mounting it into the scanning electron microscopy. This fixation can be done in two different ways. The first is chemical fixation. In this case, we typically with aldehydes first provide some kind of fixation, and later we have a more sturdy fixation, for instance with osmium tetroxide, which metallizes the membrane structures and at the same time, as we will see, allows some visualization of these structures. It also functions a little bit as a contrasting agent. So the other approach is to do cryogenic fixation. In this case, we vitrify the sample, meaning we cool it so rapidly that the water does not give time to crystallize. Because if we have ice formation, the water will expand upon the phase transition to ice, and also it will purify, meaning it will expel proteins. Of course, this will be a massive destruction to our native structure. And so cryogenic fixation means cooling down so rapidly that the sample is instantly captured in the current state, immobilized. Now, in the remainder of this video, we will focus on chemical fixation. We will deal with cryogenic fixation later. So after chemical fixation, a few further steps need to be done in order to prepare the sample for electron microscopy. First, of course, the sample needs to be dehydrated. We need to get the water out and replace it with some other material. After dehydration, we want to section the sample. We want to create thin samples. And in order for the sectioning, we first have to make sure that the sample can be easily sectioned or easily cut. For this to happen, we embed the sample in a polymer. And then finally, in scanning electron microscopy or in transmission electron microscopy without phase contrast, so if we look at forward scattered electrons, we may want to stain our sample or apply some other form of contrasting mechanism. So after the fixation and dehydration, we need to cut the sample. This cutting is done in a microtome or an ultramicrotome. So in an ultramicrotome, we typically have a sharp diamond knife which cuts a slice from the sample, very much like a cheese slicer cuts your cheese. Now for the sectioning, the elasticity and other properties of the sample have to be just right. If the sample is too brittle, it will fall apart. If the sample is too sticky, it won't cut thin enough, or it will also give artifacts. So typically we embed the sample in a polymer, so we replace all the water with a polymer material that has exactly the right viscosity, the right elasticity to have optimized sectioning with the microtome knife. Now this microtome knife, then the diamond knife, slides over the tissue block, leaving a thin section that then falls in a water bath as indicated here. These sections are then later picked from the water bath and put onto a sample for imaging, so a solid substrate, which we can use to mount in the scanning electron microscope. Now, like already mentioned, biological material in itself consists of low Z materials, which hardly gives backscatter electron contrast. In the fixation, we can use osmium, which metallizes the membranes, and then also, as it is a higher Z material, gives us sufficient backscatter electron contrast, but also other contrast agents or staining materials may be added. These may include uranyl, lead, neodymium, or other high Z materials that can be added as a salt and then are being absorbed or adhere to specific biological structures. So this gives us an image like indicated here. So clearly all the organelles and all the biological structures are visible because the membranes have been stained, they have been fixed with osmium, and this allows us to see the full ultrastructure of the sample. Now, in addition to the contrasting agents, we can also use immunolabeling to allow visualization of specific molecular components in the biological material. Of course, these molecular components can then again be indicative of a specific structure. So in the example that you see here, there's multiple cells. You can clearly see 2 cell nuclei. You can also see the cell membrane between those. And in the center, in the middle, you can see a 3rd cell of which we cannot see the cell nuclei. You can also see different biological organelles, and mitochondria may be visible, and also some other structures.